This is micro project 1. We are going to be group 3 talking about purifying hydrogen.
For our microproject, the method we selected for hydrogen purification was by palladium membrane. This process involves a steady state diffusion of hydrogen through a thin palladium membrane with one side of the membrane at high pressure and the other side at low pressure. The high pressure side of the membrane will contain a mixture of gases at high pressure with at least some hydrogen, which will then diffuse through the membrane to the low pressure side where it's contained. And then heating the palladium membrane also accelerates this process.
Pure hydrogen is one of, if not the most abundant elements in the universe and can be used as a very powerful fuel. In fact, it has been nicknamed one of the fuels of the future. This type of fuel produces zero emissions and its power production is about 15 to 35% more efficient than its combustion counterpart. Hydrogen fuel cells are very scalable. They can be scaled small enough to fit in cars or large enough to power whole cities. This type of fuel also can provide better grid flexibility. During the day where solar output is high, the abundant energy can be used to form an efficient fuel, which can be used through the night where solar output is zero. In a similar case, when wind speeds are high, the energy can be stored and then slowly used as wind speeds decrease. Overall, this levels the power grid and prevents surges, providing reliability and consistency. Hydrogen fuel cells are truly an innovative product that offer solutions to future's problems.
So why is the structure defect in diffusion important in its design and manufacturing? So the membrane that it is diffused across is a palladium membrane. And if it's in a system below 230 or 293 degrees Celsius and a pressure of 2 megapascals, it undergoes a lattice expansion, and that creates defects within the lattice that allows other elements to pass through. Adding silver to this membrane can help control the size of the palladium molecules and also help resist the changing of the lattice sites. And thinner palladium membranes allow for a faster rate of diffusion, also as lower material costs. And it leaves pure hydrogen on the other side, as shown in the next slide on the picture, where there's a high pressure side with multiple different gases, and it's diffused through the membrane and leaving the pure H2 on the other side.
What aspects of structure, defect, and diffusion would you need to understand in order to optimize its properties? For the structure, the type of membrane hydrogen is diffused through is important. The membrane needs to be permeable by hydrogen. The best material that does this is a palladium-based alloy. We can optimize the permeability through different alloys. Yttrium and silver have proven to be the most effective when alloyed with palladium. For defects, pores in the membrane used to diffuse hydrogen decrease permeability, but they also increase the strength, which is needed for thin sheets of palladium. A porous ceramic is used instead to support this thin sheet to increase its durability. For diffusion, temperature and pressure are the two main variables when optimizing the diffusion rates.
As this process clearly relates to diffusion, this has a lot of examples in the text previous. And so it's actually a form of steady state diffusion. And as you see in the figure on the right, this is figure 6.4 from Fundamentals of Materials of Science and Engineering. And this is the process which takes place while purifying hydrogen through palladium metal. The orange block you see would be the palladium metal sheet. And then as people explained previously in the presentation, where it says gas at pressure PA would be the high pressure and the gas at pressure PB would be the low pressure. And then on the left side of the block, it would be compound. And then on the right side, it'd be pure H2. And also Fick's first law applies directly to this because this is an equation to find for steady state diffusion, the mass through a given area per time. And it also is proportional to the concentration gradient, and proportionality constant D is diffusion coefficient, as seen in the bottom two equations.
What parts seem relevant to the example continued? Phase transitions are very important, which we talked about previously. Pure palladium is damaged by hydrogen embrittlement due to the alpha and beta phase transition in palladium hydride, which happens at 293 degrees Celsius. The crystal lattice structure only allows monatomic hydrogen to pass through the palladium sheet, and the crystal lattice expands during this transition, which can cause defects. And these defects, which you have previously discussed, occur during the transition, are pinhole and cracking. We've also previously discussed impurities, and the impurities are important to this because when you add silver to the palladium, it reduces the likelihood of these defects happening.